over number 3 on the review. So let's go ahead and just kind of put together our given and find right now so we don't got to keep looking back at the problem. So the ramp was 17 degrees. I should actually move that a little bit lower. Okay, we have a rocket sled thing here. So there's, okay, shooting here, all right. The mass of which I believe was 2,100 kilograms. It said that the ramp length up here was 400 meters. It said mu was 0.4 while it was on the ramp. And then, let's see here, actually, let's move you a little bit that way. Force diagram. What's force diagram on the rocket? Force gravity down. Go over there. Friction back. Yeah, force of engine, force applied, whatever the heck you want to call it. You know what? I'm gonna start to kind of break a little bit on some of like the specifics of this because you're starting to recognize there's a little bit of a free fall when it comes to like what the heck you want to call it, as long as we're honest. So I'm just gonna make my life easy and call it force F. Why? Well, that means I don't write extra subscripts. Okay, so and if you want to do that same type of thing sometimes yourself, the only one I'm not going to be okay with that is obviously on the specific ones like normal and friction and gravity. Obviously, it's helpful to do that, but if we got like a random applied force applied here, I'm going to call it out. All right, I believe that's it. Hold on, what else am I missing? 17 degrees. I didn't put the 20,000 up there. So force F is 20,000 newtons. We'll put that right on the picture. Was there anything else? Okay. So what's going to happen, of course, is rocket's going to accelerate up the ramp, and then up here it's going to take off and land over here. And the question is just a myriad of things about this particular setup. Okay. The first question that's asked of you, of course, is what is the velocity 2.5 seconds after leaving the ramp? And like I said before, obviously there's some stuff before we get there that we have to calculate individually. So I don't know exactly whether that's going to be going up or down, but it's going to be the velocity somewhere over here. Who knows? So what should we probably try to go get first? Agreed. Agreed. I don't think you're going to be able to do that first. Right, if we get velocity final when we leave the ramp, that would be velocity initial for that, projectile motion 2.5 seconds later. So that seems like a really good idea. But obviously we can't go straight there either. So what should we calculate for that? Forces. We could do forces. What's forces going to get us?
We get acceleration.
We get us acceleration. Okay. Why would acceleration be helpful here?
Because you'd be able to get the velocity initial of the acceleration.
In what way?
Kinematics.
Yes, correct. You'll notice that you actually currently have two kinematic variables while it's on the ramp. You know what the initial velocity is because it says it starts from rest, and you know the displacement of the ramp is 400 meters. So we just need a third kinematic variable. Right? So you think about what were my kinematic variables else that I can calculate. Obviously, we want VF, so my other two options are time. Can I calculate time? I can't think of a way directly. Can I calculate acceleration? Yes. So we're going to sum the forces on this guy in order to get the that thing. So let's go ahead and grab this real quick. Okay, copy. Go to another page and paste. All right. So, we need to find its acceleration. What should I probably do first? Yeah, we got to shift the axis. Why do we have to shift the axis? So acceleration is on an axis, yes. So it is not in 2 dimensions, or so we can get that. Yeah. So let's go ahead and erase this too. All right. So I've shifted the axis now. How much did I shift the axis, by the way? 17 degrees. Which way? When you do this, it's clockwise or counterclockwise? Be counterclockwise. Yep. Okay, most important piece of this, obviously you'll kind of notice that really nicely force normal, F, and force friction line up pretty much perfectly, so we don't have to worry about that. But of course the main thing is force of gravity right down here. Because that axis used to be straight down, we of course need to come down here, and this is the immediate thing you do when you shift the axis. You'll notice again, when I do it, I just go straight down to the force normal and perpendicular, but you want that little guy right there. And what angle is that guy right there? 17 degrees. And the other thing I would probably do if I were you is just make this triangle down here. Okay? And I say make the triangle. You're making a right triangle. So that would be that side. That would be that side. Here's your right triangle to show us that force gravity, here maybe it is, with the new axis, force gravity is in what quadrant? Third, correct. Meaning both its x and y are going to be negative. All right. So we're summing the forces. Where do you want me to sum the forces first? What's that? X? All right, let's do it. Let's sum the forces in the x. Is it accelerating in the x? Yes, I agree. Okay, so it's accelerating in the x, so I don't need to touch that. What is the sum of forces in the x? Positive F, because it's straight there. Negative force friction, because it's straight there. And negative force gravity in the x, because this force is acting in the x in the negative direction, but it is not only in the x, it is also in the y. That's why we put that little x on there. Meaning, by the way, that when you do that, technically this right here is the piece that you're actually looking at. So, we're looking for acceleration. Do we have mass? Yes? Do we have force gravity in the x, or can we go get it? Yes, we can go get it. We, of course, know F. Obviously, you're seeing. We know force friction. No, we don't currently know force friction. So we're going to need to go get force friction first. So I'm going to put a pause on this right now. Where do I need to go? What do I need to go do in order to get force friction? Sum the forces in the y for the specific purpose of going to find what? Force normal. Then we can use the model of mu to pull us that friction, and then we're good to go on this. So here we go. Sum of the forces in the y equals mass times acceleration in the y. Is it accelerating on the new y? No, it's not accelerating this way at all. Acceleration should be straight up there. So that means that this is 0. What are the forces acting in the y? Correct. Signs on those? Negative force gravity in the y plus force normal is equal to 0. So force normal is equal to force gravity in the y. And looking at that triangle again, I'm just going to blow this up. Here's force of gravity, which of course is equal to mg. Here's your triangle. So what trig should I use to get force gravity in the y? Cosine, because it's adjacent. So I come over here, mg cosine of 17 degrees. Of course, you can plug in numbers whenever you'd like. Okay, I know there's a simple step to this next part, so I don't have to write extra numbers. Okay, this is just kind of a hint so you don't spend a bunch of extra time doing something when you're going to do it again in just a second. So here's my suggestion, but you can do whatever. Okay, you could plug numbers in right now. You have that option. I would immediately go to this. Force friction is equal to mu force normal, and therefore equal to mu times mg cosine 17. And if you want to plug in numbers, let's go ahead and do it right here as opposed to before, so you're not doing it like twice and like taking extra time. Again, me personally, I would probably usually just take this whole equation and put it up there for force friction, but I know that can be a little bit extra, so let's go ahead and put this in for people here. All right, what do we get? So this, if you did it individually right over here, would be 19,680, but times 0.4, we get that friction is 7,872 newtons. Let's just go ahead and actually 3 sig fig, so 7,870. Now we can come back up here. Now that we know force friction, we can just kind of do some basic algebra here. Let's go ahead and, since we have these two numbers, let's go ahead and get force gravity and the x separately real quick. Again, you could put it right in there, but how do we get force gravity and the x? Mg sine of 17, okay? And that's, of course, this piece right here. So that's going to be 2100 kilograms times g times sine of 17 degrees. That's going to be 6,020. And again, I'm rounding there. Now, the only simple thing I need to do, and I'm going to use the whiteboard for it, and I wouldn't mind if you did kind of something similar, is divide both sides by mass. So let's plug our numbers in. F is 20,000. Force friction was 7,870. Okay, force of gravity in the x is 6,020. And mass is, of course, 2,100 kilograms. So acceleration is equal to I got 2.91, yes? Pretty close to, I mean, there's a little bit of rounding there, probably. And we are nowhere close to the answer to part A. All right, so what's that acceleration allow us to do now? Correct. I'm going to go back to the main thing right up here. Remind ourselves that we actually have on the ramp, we know these variables right here. We know velocity initial. Actually, no, I'm not going to do that here. I lied. And we'll go back to this page, actually. Here we are. Let's go down here. We know that velocity initial, let's use it. I'm going to use a different color because we're at a different section. What color do you want? What? Blue. Good choice. Okay. Velocity initial is 0 meters per second. We know the displacement is how much? 400 meters. And we just found the acceleration is 2.91. What lets you know that this is one-dimensional kinematics? That's a fancy way of saying it, which is 100% right. Straight line, yeah. Goes in a straight line, you can always shift the axis so that it's on one-dimensional problem. Okay? Hello, sir. What do you have?
A cookie for you.
That is amazing. I appreciate that. I don't believe that. All right. What are we looking for? Velocity final, yeah. You remember when you guys thought kinematics was hard? All right, moving on. Like, seriously, some of you were like, kinematics is hard. And like, now you look at kinematics and like, oh, thank goodness. Boy, this is going to take like no time at all and we know how to do it. All right, what equation do you want?
Velocity final squared equals velocity initial squared plus 2 times acceleration.
There you go. What'd you get? I got 48.3, but yeah, sure. Only reason I'm being pedantic here because you were 100% right. It's because I'm pretty sure that's what it says on the answer key in case anybody's like, yes, you agree. All right, now, technically speaking, by the way, okay, for the sake of the next problem, if we look back here, what is the velocity technically at this spot? It's 48.2, agreed, at nope. I am looking for an angle. 17 degrees, right. Because it left 17 degrees above the horizontal here. All right. Now, the question of part A is what is the velocity 2.5 seconds after leaving the ramp? So this was velocity final, obviously, for the ramp. What is it now? Velocity initial for the just simple, okay, I say simple, we've gone through sum of forces and we've gone through one-dimensional kinematics, and now we're at 2D. Because if you look at the force diagram, okay, you'll notice all three of the other forces, well, three of the other forces go away, right? Force, because the force of the rocket, because it straight up told us that's when they turned off the rockets. Okay, force normal because it's not on the ramp anymore, and force friction because what type of friction is this again when we put it in a problem? Surface friction. So again, you're not on the ramp, and we're not worrying about air friction. So the only force left on it is gravity. And remember, projectile motion is when an object is only under the effects of force of gravity, but moving in the x and the y. So here we are at two-dimensional kinematics. So let's go ahead and highlight. Oh, what are you doing? Where'd you go? I didn't want that at all. Cool. Copy. Paste. Perfect. All right. So here we go. New color, new type of problem. What do you want?
Pink.
Pink it is. Lighter or a little bit darker? Darker it is. All right. So x, y, velocity initial, velocity final, acceleration, time, and displacement. Okay? So what goes where?
Velocity initial is 48.2.
Which one?
In the both hundred to do cosine and sine.
Correct. Yeah, you got a good trick here because that's not in the x or the y. So how do we figure out how much is in the x and the y? Let's just go ahead and do those separately because I'm pretty sure we're just going to want the numbers and not have the equations a bunch. So how do we get how much of this is in the x? Yeah, so this is going to be 48. Velocity in the x is going to be 48.2 units, dummy. Meters per second cosine of 17 degrees, and velocity initial in the y is going to be 48.2 meters per second sine of 17 degrees, and that'll go there, and that'll go there, and tell me what we get. First one is 46.1 meters per second x hat. 14.1 meters per second y hat. Okay, what else we know? Acceleration in the x is 0. There are no forces acting in the x, so it's 0. Okay, and what is it in the y? Almost. Don't forget we got vectors again. Negative g. Don't forget, yeah, it's kind of hard coming out of energy a little bit because you have to remind yourself, oh crap, that means we have to pay attention to vectors again and do signs and all that, but yeah. And again, the other piece of that is don't forget that g is not negative. We make it negative by defining up as positive, down as negative, blah, blah, blah. What else you got? Well, sure, but I mean, if you want, I usually just do something like that. You're welcome to write it down. Okay, you're welcome to write it down now. But I think there's a better one to write down. Time, yeah. Time is 2.5 seconds. And what are we looking for? Velocity. Keep in mind, this is not, once again, this is not velocity in the x, this is not velocity in the y, this is velocity. But what it's actually looking for is this whole thing, and if it says velocity, it wants us to do that trig to work all the way back to both speed and direction. Yes? Now, I already pointed out correctly that we have the x, so we simply got to go get the y. How do we go get the y? It's actually a pretty easy equation. What equation do you want? Velocity final in the y is equal to velocity initial in the y plus acceleration times time. So this is going to be 14.1 meters per second y hat plus a negative g times 2.5 seconds. and you get negative 10.4. What does that number mean? At about 10.4 meters per second. Is that how fast the object is moving? No, because also moving in the x. So that means, by the way, I highlighted this a second ago, but actually it does mean it's about right over here. And if I do some quick analysis, kind of to understand these numbers, I can tell you a couple things. One, obviously it's over on the right side because it's heading down, but two, I know it's actually above the original spot it was launched. How do I know that? So very, very close. It's not at the same magnitude as what it was going up yet over here. Not that that matters, but it kind of gives you an idea of roughly where it's at. So it's probably just a little bit above somewhere over there. So right now we are, just kind of use blue for the velocities, finding this. And negative 10.4 is this piece right here. And 46.1 is this piece right here. So what do we do to get the actual velocity? Pythagorean theorem will give us the speed. And since it says velocity, we know we also have to get direction, right? So how are we going to get direction? How are we going to get the angle? Inverse tangent, yeah. Okay, so here we go. Velocity final is equal to velocity in the x squared plus velocity final in the y squared. We square root that. That's just your Pythagorean theorem. Also, by the way, since it is almost back to the beginning, I would guess it's really close to 48.2, but slightly less. What'd you get? Sounds about right. No, I got 47.3. Yeah, and actually, you know it's not 44. Here's why you know that. Okay, and I think I know what the issue is. Okay, if it's 46, if one side is 46, Pythagorean theorem says that your hypotenuse better be bigger than both sides. My guess is, and I'll remind you of this, you probably just put the negative in a weird spot that it didn't cancel. So a reminder, when I punch in Pythagorean theorem into my calculator, I will write the negative as the work, but when I punch my calculator, I know it cancels anyway. So I don't have to be careful of parentheses. I just plug in positive both cases because I know it's canceling anyway. But I got, yeah, 47.3. And that is the speed, that is the hypotenuse of this triangle right here. But now we need the angle. How do we get the angle? Inverse tangent of negative 10.4 meters per second over 46.1. That's y over x. And you get negative 12.7 degrees. And almost more than halfway through class, we're done with part A. B, C, and D definitely go a lot faster, especially since there's no collision in the middle of the year. All right, questions, concerns about this? Okay, moving on. B, find the max height from the rocket sled. Okay, a couple things to point out here. Max height is going to be this guy right over here. Okay, please note that originally when I did, we're going to use basically two-dimensional kinematics, sort of. All right. When I did it just a second ago, this was my initial, and this over here was my final. If I change where I'm looking at, can I use the same set of variables? I can't. It's not the same time to get that spot. That's not the same velocity final up there. Those aren't the same displacements, so you can't. But maybe this is what you're saying. There are certainly numbers that you can repeat. What numbers can we repeat if we're going to the top? Let's change color here. Let's go green now that we're trying to get to the top. What numbers from this previous set can we use now in the new set? acceleration and, yeah, my velocities, my initial velocities are still exactly the same. So acceleration is 0 and negative g. And my initial velocity in the x was 46.1 meters per second x hat and 14.1 meters per second y hat. So those are the exact same initial conditions that we had in the last problem. The only difference is we need to change where we're looking. What number do we put up here to specify that we want to go to the top? Correct. Is going to be 0. This makes sure in the problem that's where we're going. Can we immediately now go get delta y? Yeah, we can get delta y. Why can we go get delta? Because we already have 3 variables over there. So what equation do we have that will get me what I want? Oh, not that one. Also, make sure when you're doing two-dimensional kinematics, you definitely want to have y's and x's in it. Notice, yeah, I'm switching to delta y over here. My velocity final will cancel. I'm going to subtract VIY on both sides. Sorry, VIY squared. And then divide by 2a in order to get delta y. So this is going to end up as negative 14.1 meters per second y hat squared. Does the negative cancel there? It does not. So that's not inside the squared, but that's good because right down here acceleration is going to be negative g, so then it will cancel because of that right there. Calculate all that out. You'll end up with 10-ish, isn't it? What'd you get? 10. I'm gonna go 10.1. All right, is that your answer? Let's go back to the picture real quick. Is the answer of how high this rocket is in the air 10.1 meters? Definitely not. Why do I think that? Well, I just took off 400 meters, a quarter of a mile up a ramp. And you're saying I only went 10 meters in the air. What is missing here? Let's do this in the picture. What is that 10.1 meters? Where should I draw that here? That is this. That's how much y has changed. Now there's a very easy solution to get the rest, but we're missing this. What simple thing can I do to get that? Trick. You know the total ramp height, as we said earlier, was actually this 400 meters. You know that angle is 17 degrees. So pretty basic trig is going to get you the height over there. What do you got to do? Yep. So let's say the height initial is equal to 400 meters sine of 17 degrees. This is where most of the height's coming from, isn't it? 117. So if we want an equation for the answer to be the height final is equal to the height initial plus the change in y, or if you prefer, the change in height. Height initial is 117 plus the change in height is 10.1 meters. If I do appropriate sig fig stuff, I should actually drop the decimal over there, so it's 127. Or if you said 127.1, dealer's choice. Look, B went way faster. B went so much faster than A. Okay. Next. Let's go ahead and grab this again. Well, actually, hold on. Now, cool, grab the right one. The next thing, use energy. Now, this used to be a little bit more complicated when there was a bird thing up in the air. Okay, there's no longer a bird thing in the air, so you used to have to do some stuff in the middle right here. You don't have to worry about it. So all we have to do is use energy. The great thing about energy is scalar. You could 100% find the speed using 2D kinematics, but if you do that, you got to put the x, you got to put the y, you got to do all that stuff, you got to combine it back together. The great thing about energy is all you got to do is what we've been doing last chapter. First, think about the force diagram. What's the force diagram? That's it. Force gravity is just down, changing colors again. Let's go to peach. Cool. All right, force of gravity down. So, is that a conservative force? Yes, it is. So that means the only thing doing work on this is a conservative force. So what nice piece of energy should we probably do? I would say conservation of mechanical energy, right? So here I go. Mechanical energy initial equals mechanical energy final. What energies are changing in this situation? Three mechanicals, of course, are gravitational, elastic, and kinetic. Which ones are changing? Kinetic, sure. And is elastic? Huzzah! Anything cancel here? Gravitational final. This is basically the exact last problem of your test the other day, right? This is 1/2. This is the Ash problem. Do we actually need to know what the mass is? Nope. Cancel, cancel, cancel. Multiply 2 across everything. I'm just going to multiply it individually so that this ends up as vi squared plus ghi, sorry, 2ghi. And then we'll square root the whole thing and plug our numbers in. Now, as I said, it's scalar. So what is vi in this setup? $48.2. Do we need to worry about the x or the y here? No, scalar, so we don't have to worry about it. So plus 2 times g, and what was height? What's that? No, that's not true. I am starting, this is an important note, I am starting here, right? If you wanted to, by the way, 100% you could start up here, in which case your initial height would be 127, but what would your initial velocity be if you started up here? No. It would be 46.1, because it would still be moving in the x. Both will end the exact same way, but we've already got it set up from here, so what should my height initial be? Yeah, same. And you end to hit the ground with, I got 67.9. Can confirm? What'd you do today in class? One problem the entire time. Well, we almost ran out of time. All right, so finally part D. The last thing it asks for is simply calculate the delta x from the ramp, at the end of the ramp to where the rocket lands. Again, when there was a collision in the air, this was a little bit harder because you actually had to do it in 2 separate spots. It's actually pretty easy now because, once again, it is simply just a 2-dimensional problem. The main thing to keep in mind here, though, is, once again, I'm starting here, but the first problem ended here. The second 2D kinematics ended here. Where do we want to end now? Over here. So can we use the same set of variables? No. So for the last problem, switching colors one last time, what have we not used? Teal. Green doesn't show up really well. Light green it is. Teal, right? Or this green, you mean? We use that at the very beginning. Teal it is. All right. But well, just like before, we can. What numbers are going to be exactly the same still? Acceleration is going to be 0 in the x. Is going to be 46.1 meters per second x hat, just like before, and 14.1. Is that correct? How much of your pages is taken up? What are we talking about? 3/4, the whole thing, 2 pages? Where are we at? 2. Some of you write bigger than others. That's better. All right. Now, the last thing to ask is, how do I tell the math I want to go there? By the way, if you wanted to, you could technically split this still up into 2 separate problems on the way up and on the way down. It's just going to be a little bit more efficient to do it this way, but you can do the other way as well. Okay, it still should work. How do I tell it that we want to end there? So close. I'm not going to say height. We know delta y. What should delta y be? No. 0 would put us here. Correct. It should be negative 117. We want delta y to be that. So this should be negative 117. And how do we get delta x? Yeah, which means you got to use this beast. We thought we could get away from it, but here it is again. And you're going to plug your numbers in, and here's what you're going to end up with. You're going to end up, well, actually, does anything cancel here? Does delta y cancel? Does acceleration cancel? Does velocity initial cancel? So how do we have to solve this particular algebraic problem? Stupid quadratic. There it is. Yeah, just a gentle reminder, if this quadratic does still elude you for some reason, there is a kind of a shortcut to a certain degree. You can go find velocity final in the y first. Keep in mind that it does need to be negative, and then you can go get time, but honestly, it's the exact same thing. So here's what it is, okay? Whenever I set up quadratic, by the way, just for those of you who didn't get it, here's how you know it. Variable that you're looking for to the second power. Variable that you're looking for to the first power. Variable technically to the 0th power, aka there's a constant that you can't see. If you have all 3 terms, you know it's quadratic. If that's the case, I highly suggest you order it like such. Just put it all on one side. Now, usually I move the delta y over. Actually, you guys might have noticed, acceleration is always negative. So what I'm going to do is I'm going to move this over this way. I'm going to get g over 2, just adding that on the other side because it was negative. And you know what? Let's drop the delta for a second. Let's just make our life easier here. And then we subtract this, which is going to be negative 14.1 meters per second t. And then now we don't have to do that, but that's just going to be negative 117 meters is equal to 0. And what's your b term? Sorry, I should probably go in order. What's your a term? And g over 2, or 1/2 g. What's your b term? Negative 14.1. What's your c term? Negative 117. So here we go. Minus b, plus or minus. You don't have to write this out. I don't care, but I'm just putting it up here for reference. So this should be minus the negative 14.1 meters per second plus or minus the square root of negative 14.1 meters per second squared minus 4 times g over 2 times negative 117 meters. All over 2 times g over 2, 2's cancel. So we go to that side over there, 14.1 squared. Minus 4 times g over 2. Square root the whole mess. Always do that part first. And this ends up as 49.9 meters per second. Then you'll notice this is going to be a positive here in just a second. So I could add, I could subtract, but you'll notice if I subtract, I'm going to get a negative time. Obviously, that can help us. So I'm going to take 14.1 plus 49.9, then divide by 9.8, and I get 6.53 seconds. You are welcome to find the other time, but as I mentioned before, it's going to be negative and unhelpful. And what's the last piece of this puzzle once I have the time? Nice thing about delta x is since delta x is constant, we can just use the constant equation. And what's the velocity in the x? $301. I'm gonna go ahead and go out on a limb and say that some of you actually might want this work. So I'm gonna put the QR code up in case you are interested, as well as obviously we'll post the video as well. I'm gonna stop the video now.